Hello, everyone. Thanks for being here. This talk is about the acronic analysis of language, but actually I'm working on temporal dynamics in personalized information retrieval, and in general I'm interested in every kind of time-related process that is going on natural language processing and information access. Language is something that is live, because we use language for communicate, so it has to reflect the world that surrounds us. So it usually undergoes some change and evolves over time in order to serve this purpose. So for example, if I was saying the sentence surfing the web like 40 years ago, people would have taken me like crazy because the web wasn't invented yet, and the verb surf wasn't used yet in that meaning. So the diachronic analysis of language actually looks at these phenomena in order to understand how language evolves. It is also called historical linguistics. And this is a different perspective to consider language in opposition to the synchronic analysis, where actually we look at the language in a specific timing point. This kind of analysis led us to understand why language changed, to reconstruct the prehistory of some languages, like for grouping a category of languages together. It led us to develop some theories about the language changes and describe the history of speech communities and also etymology. But this kind of analysis is usually performed manually, so it's very expensive. The point is to automate to some extent this process. And in our help, Google developed in 2009 the Google book Angra. This is a huge amount of information, of historical information, because it's about a book published since 1500 until 2012. The second release actually of this dataset was in 2012. It's about 5 million books, and is about the 4% of all books published on Earth. So the Google Book Anagrams is a sequence of anagrams. It can be just one unigram or bigram up to 5 grams. And in total, it accounts for 500 billion words. So it's actually a lot of information about our history that we can look into in order to understand what's going on. And this is something that people have done already. It goes under the name of culturomics, and is a way of looking at this huge amount of data in a quantitative way in order to understand human behavior or cultural trend. And this can tell us something about what's going on and can help us, for example, to understand some grammar evolution. So it seems like at some point the verb burned took over from burnt. Or for example, about popularity of some characters or people, like Mickey Mouse, Marilyn Monroe, Che Guevara, and Neil Armstrong. Or about some phenomena like feminism, and how he had an upsurging frequency during between 1900 and 1920 in concurrence with the suffragette phenomenon. It can also tell us something about censorship. Like, for example, the term Marx Chagall was actually dropped out from book during the Nazi censorship in Germany. Or, for example, other kind of events, like the terms associated with influenza, like Spanish flu, Asian flu, or Russian flu. But all of these analyses are based on the frequency of terms in this huge amount of data. So they can tell us some story, but not all of them. For example, let's consider this plot. These are the two Italian verbs, chiamare and telefonare, that have translation in call and phone in English. So basically, the verb chiamare at some point started to take on the meaning of make a call, phone someone. But you cannot infer this kind of trend from this plot. because it's not evident. Actually, it seems like the verb chiamare at some point has started a slow decline in terms of frequencies. So we need something more powerful that can tell us this kind of story. That's the reason because I'm looking to distributional semantics model that are a way of representing the semantic of terms through some word space, some geometric space. The theory behind this distributional semantics model is based on these three important people. First of all, first, that gave us some insight about how to infer automatically the meaning of a word through its companions. That means through the co-occurring words, actually looking at some corpora. And Wittgenstein actually told us, okay, the meaning of the word is actually how it is used in this corpus. So you can look at the companions, but you have to look at its use in its normal use in language. And Harris gave us some information about how to model all of these through some mathematical structures of language. So basically, the distributional semantic models tell us that we can build a vector space by looking at word usage in a corpus, and looking at the companions of this word in this corpus. And this vector space that are called semantic space or word space, the similarity between words is actually translated in the closeness between words. So closest words are also similar to one another. But there is a problem with this kind of approach, because actually they are the snapshot of the corpus in a specific time moment. So they don't take into account the temporal information. So my step is to actually broaden this definition in a way that we can actually account for this temporal information. Let's start with a specific distributional semantic model that is called random indexing. This is a very simple technique for building this kind of word space, where we basically assign a random vector to each word in the vocabulary. These random vectors are very high dimensional, sparse, and ternary. Means that they can take on just three values, -1, 0, and 1. Then we can build a representation for each term that we call in this context semantic vector by summing the random vector of the co-occurring words in the corpus. So we go to the corpus, we define a window of text that we want to consider, like, for example, 5 words before and after the target words. And we sum the random vector associated to that companions every time we found our target word. We can extend this random indexing in order to consider the temporal information in a very simple way, because the space is actually represented in terms of its basis, and in this case, these are the random vectors. If we take a corpus with temporal information and we split this corpus in a different time span, then we can build a random indexing. We can build a word space on each corpus for each time span using always the same random vector. And in this way, we can compare words from one space to the other. So for example, we have a corpus of 40 years. We split in 4 corpora of 10 years each, and we build this word space. And then we can compare, for example, the same word in space 1 and in space 4 and see how similar the same word is with itself. And if there is a high variance in its component, it means that this word has been used in 2 different contexts. So it has 2 different meanings. But we can compute also the similarity between words and see how these change over time. So for example, in 1910, the term telefonare wasn't invented yet, but then it appeared in 1920, and this was very distant from the word chiamare, call. But as we go along the timeline, we see that they start to become close to one another because they start to be used in the same context, interchangeably. So with this kind of information, we can actually build some plot and derive some information that tell us another story. This is the first plot. Okay. Okay, this is the first plot that I showed you before that wasn't giving us too much information. And this is actually a plot built by plotting the similarity between call and phone, chiamare e telefonare. And okay, at this point, the term telefonare wasn't invented yet, then it started to appear, but then we see that after 1920, it has a very high similarity, 1 year after the other. So it actually means that they are synonyms. So how can we use this information to understand how language change? We basically should have a corpus of temporal information, with timestamp. Then we have to choose beforehand how to split this corpus, how big has to be the time span. Then we run the temporal random indexing algorithm on each time span. In this case, we consider 10 years. And we have the different word spaces. For each time period, we extract a number. This is the number of our time series. And then we can detect changing point through some change point detection algorithm. So first step is defining the time series. In this work, I've defined 3 different ways. This time series, the first one is based on log frequencies. That is basically the frequency of the word in each time span. And the second 2 are based on the temporal random indexing. So I'm computing the similarity of the word with itself. The first method is pointwise, and is basically comparing the similarity of the word at the time k with the semantic vector of the word at the previous time. In the cumulative approach, actually, I'm comparing the semantic vector of the word at the time k with the sum of all the semantic vectors for the same word in the previous time. And then we need a way for deciding when there is a change or not. So we decided to employ this change point detection algorithm that is called the mean shift model. Basically, given a time series, it normalizes its value by the mean and the deviation. So we have, at the end, a z-score series. So after that, we can compute the difference between the difference pivoted at the time j between the series before and after this time. We are basically computing here the difference between the mean. So it means that if this difference is huge, there is a huge difference between the mean of these 2 time series. So there is a gap. But how we decide if this gap is significant or not? So we use a bootstrapping approach under the null hypothesis that there is no change in the meaning. It means that we permute all the combination of the time series, computing every time this kind of statistics, and then we compare the p-value between the first one and the permuted time series. If the difference is significant, then we have our change point. So we have done an evaluation, a preliminary evaluation in Italian Google Ngram. We don't have actually data set for this, benchmark for this, so we had to build our own benchmark. That means going through dictionaries and manually annotating words that have changed their meaning, or that have took on some new meanings. So we use the pull technique, taking some terms that we suspected to have undergone this kind of change, and then we manually checked dictionary like this in order to see, for example, if there was a new entry in their meaning. So in this case, for example, 2001 is a change point for this word, girotondo, that is a political movement. And in order to see if the algorithm correctly detected that change point, we consider right the indication of this word with a time that goes after 2001. So we have conducted a preliminary evaluation in terms of accuracy using the temporal random indexing with the pointwise and the cumulative approach and comparing it with the log frequencies. Moreover, we also compared it with other two ways of building this random indexing that is called reflective random indexing, but they give actually very poor results. What's interesting is the gap between the log frac approach and our temporal random indexing approach that is kind of huge. As I mentioned, this is just a preliminary work because we want actually to expand this work on English language, on the English Google Angra. And for doing so, we need to collect information about when words in English have changed their meaning. So, for example, we are now looking at some etymology dictionary in order to see if there is some new added meaning. But this is a very time-consuming work, so if anyone wants to work on this kind of problem, is more than welcome. But this kind of approach is not just limited to the diachronic analysis of language. You can actually apply it on other interesting tasks, like, for example, looking at trends on social media. In this case, we have used Twitter, a collection called Twitter that spanned from 2012 and to 2015, and it has about 500 million tweets. So this is an Italian collection again. I'm sorry if all the examples are in Italian. But we have looked, for example, to the word Grillo, that is a politician, with two emoji called happy and sad, to see the trend between these two. So this actually is telling us the similarity between Grillo with sad face and the similarity between Grillo and happy face. So sad face is winning. But the same thing happened with Renzi. So it's like politicians are much more associated with bad things. Another interesting experiment came from the association between Raggi, another politician, is actually now the mayor of Rome. So this is the correlation, the similarity between Raggi and Rome, the blue one. The red one is the similarity between the movement, the five-star movement, and Raggi. So when Raggi started to work in M5 star, there was a gap between these two, because actually she had not entered the campaign yet. But at this point, you see that there is a rise in the trend. And actually, the difference between these two becomes smaller and smaller. That's the moment when actually Raggi decided to enter in the local election for Rome. And you can see another trend here between when there was a crisis for the Marino. Marino was at that time the mayor of Rome. So you can actually detect nice trend from tweet or whatever kind of social temporal based information that you can collect. So I'm actually now organizing a workshop on temporal dynamics in digital libraries. So if you are interested in this topic, just keep in touch with me, or maybe just decide to join us in this workshop. Thank you. I hope I'm quite good.
What's the training time for the Twitter database, for instance, of one of the two plots you've shown us?
Can you talk a bit louder, sorry?
Okay. how long does it take to compute the similarity for the Twitter database, for instance?
I don't know how long it took, but I can tell you that it was computed on a single server with 32 gigabytes of RAM. This technique is not very high computational demanding. It can be run very easily on every computer. And I think it took, like, in that case, less than 1 week. But again, it was running on just one server. I don't know even if I can call it server, really, just on one machine. And yeah, the problem in that case is computing the similarity between the different time spans. So in this case, you are, for every label on the x-axis, you are computing the similarity between these two words. So it's not much more computational demanding, but the problem is in building the space itself, because you have to keep in memory all the vectors, and that can be a problem. So yeah, with respect to other techniques like word2vec, they can give better results without this memory issue that you can have with random indexing. But in that case, you don't have the comparability between spaces. So you need some alignment technique.
Hi.
Okay.
So you showed the random initialized vectors.
Yeah.
The size, is it the size of the lexicon? Or?
No, the size of your memory. So, for example, in this experiment, I think we have set up the dimension of vectors to 1,000, but that's a very high dimension. For other experiments, we set up it to 200, 500 is usually a.
So it's highly sparse. Only 3 entries are initialized.
No, that's the seed number. You have to decide how many seeds you want in your random vector. Usually, we used like 10 seeds. So up to 1,000 components, you have just maybe 10 components that are different from 0.
And each vector represents a word in the window.
Each random vector is assigned to a word. Then after the computation of the semantic vector, you have a reduced vector. I didn't show you too much insight into this part, sorry, but the point is that when you are summing the random vector associated to a term, you are actually, is the equivalent thing of multiplying the original matrix with a random matrix that reduces the dimension of the vector space. So you end up, for example, if you set up the dimension of the vectors of the random space to 200, at the end you will have a matrix that is the size of your vocabulary per 200. That is the random vector size.
Is it like a word embedding representation?
It's kind of, it came before word embedding. Yeah.
Yeah, it's really cool. More like a comment. Just a few weeks ago, there was a paper in Science that looked at the biases inherent in GLOVE, the Stanford word embedding data set. And I think what would be really cool is to see these biases many of these biases that are inherent in our culture, right? The social norms and biases, how they've developed using your technique. I think that would be really quite insightful, I think.
Yeah.
And one question I have is, how do you focus on certain words? Like, do you have a preconceived notion what you would like to compare? Like you had political examples?
This Twitter data set was collected actually with the seed of words that were political. So I knew that domain was that one, and then I started to query with political questions. But otherwise, you should just look at the domain. Collecting tweets from Twitter means that you have usually some search query for which you crawl the information. So in this case, that's the reason. But no, you can actually look for whatever. I didn't show these results here for the, okay. No, it's not here. Okay, for another work that I showed 2 years ago, we actually looked at the words that changed semantics, and then we started to look at the documents that we had at hand, and we found very nice, interesting things that they were pretty naive with a post perspective, but I've never thought about them. Like, for example, the word cinematographo, that he likes cinema. It was the original word for cinema. And then at some point it started to not to be used because the verb movie, that is in movement, started to appear, and it was much more trendy. So you can see this kind of trend from data. But actually, in that case, the words went out from just querying the data set itself, not knowing at priori what kind of information we're looking for.
Thanks for the talk. Would it make sense to segment your corpus by topic in a sense, so that you see that, I don't know, I know grillo, so like it's an animal in the original term, so you pass from the topic of nature to the topic of politics. So does it help in the recognition of a change?
No, really, no, really. What you can do is if you know that some word undergoes some meaning change, at some point, then you can focus, for example, with a fine-grained split of temporal periods in that case. Like if I know that some event happened in some specific time, I can split the data in a way that reflects this kind of change. But segmenting data by topic doesn't help in this kind, for this kind of analysis.
So I would say by time and by topic, say.
You can do by time, and then you can cluster information by topic and see how they are related to one another. Yeah.
Thanks.
Thank you.